Welcome to lesson 26, Gas Laws and the Ideal Gas. Today we turn to gases. Here's the plan for today. Firstly, and most importantly, what is gas pressure? It's basically when the molecules hit the side of the container. It's the force per unit area that the gas exerts on the walls of its container, caused by countless molecules hammering into those walls. Hold that picture as it explains everything that follows. Now the three experimental laws. Each holds one quantity constant and looks at the relationship between the other two. First, Boyle's law. At constant temperature, pressure times volume is a constant. Squeeze a gas into half the space and the pressure doubles, the same molecules hitting a smaller area more often. Charles's law. At constant pressure, volume over temperature is constant. Heat a gas and it expands. And the pressure law, or the Gay-Lussac law. At constant volume, pressure over temperature is constant. Heat a gas in a sealed rigid container and the pressure climbs. The molecules move faster and hit harder. That's why an aerosol can carries a warning about heat. If a gas expands at constant pressure, it does work on its surroundings, and that work is P delta V, pressure times the change in volume. Say the gas exerts a force on one of the sides of the containers and pushes it out by a distance d. We can rewrite the force as the pressure times the area, so the total work is pressure times area times d. This area times d collapses into the change in volume, so the total work is the pressure times the change in volume. How do we know molecules are really there, jostling about? Brownian motion. Look at smoke particles in air under a microscope, and they jiggle around on erratic, random paths. Something invisible is knocking them about, the air molecules themselves. That was some of the first direct evidence that molecules exist and move randomly. Now, molecules are absurdly numerous, so we count them in bulk using the mole. 1 mole is Avogadro's number of particles, 6.02 times 10 to the 23. A little history explains the odd definition. Originally, it was meant to be 1 gram of hydrogen 1, but that's imperfect because hydrogen has an isotope, deuterium, hydrogen 2, so the mass isn't clean, so it was redefined against 12 grams of carbon 12 instead. And the molar mass is simply the mass of 1 mole of a substance in kilograms per mole. 1 mole of oxygen gas, O2, is 32 grams. Now the payoff. Let's combine all three laws. Boyle links P and V, Charles links V and T, and Gay-Lussac links P and T. Put them together and you find that PV over T is constant for a fixed amount of gas. Turn that constant into something measurable. An experiment gives us R, the molar gas constant, 8.31, and we scale by little n the number of moles, and there it is, PV equals nRT, the ideal gas equation, one equation containing all three gas laws at once. There's a second form that you must know as well. Instead of counting in moles, count the actual number of molecules, capital N. Then the constant changes from R to little k, the Boltzmann constant, which is just R divided by Avogadro's number, so PV equals capital N KT. Two forms, same physics. Moles with R, molecules with K. Chop and change between them carefully, depending on what the question gives you. That's the end of the video. Thanks so much for watching and check out my tutoring page below.